Okay, so good evening, everyone. So today we are in the week 4 problem solving session of this NPTEL course, NMR Spectroscopy for Structural Biology. So I hope all of you have gone through the week 4 lectures. So last class we had discussed about FT NMR, Fourier transform NMR mainly, the practical aspects of FT NMR, the dynamic range problem, then how analog to digital conversion ADC digitization is done, how the information is stored, and we had also looked into the detection axis. We had seen quadrature detection, single carrier detection, right? So today we will revise the concepts which were discussed in the lectures on water suppression, solvent suppression, methods of solvent suppression, why is it necessary. Then we will revise the concepts that were discussed related to spin echo. Then nuclear Overhauser effect (NOE), and in the later part we will also talk about uh, the spin polarization. So we will quickly revise the concepts that were discussed in polarization methods, spin polarization, inversion, and INEPT. Okay, we will go through those concepts, and we will also solve a few questions that will help you to solve the assignment and also make the concepts more clear. If you have any doubts, you can ask me. I will wait for 1 or 2 minutes and then start the session. Okay, so I'll start sharing the slides. So I hope the screen is visible. I'm audible as well. So okay, let's start. Good evening, everyone. I'm Akash Jyoti Pathak. I am a PMRF PA for this NPTEL course, NMR Spectroscopy for Structural Biology. This course is it is a rerun course and has been taken by Professor Ashutosh Kumar and Professor Ramakrishnan Hosur. So, today we are in the week 4 problem solving session of this NPTEL course. So, first we will start with solvent suppression methods. So, in the last class we had discussed about this concept about the dynamic range problem, right? So, what happens is that when your sample is in a solvent, the proton peaks of the solvent are so high that it can suppress the signal from the sample, or it can suppress the proton signals of the sample. So what happens is, in a typical proton NMR experiment in water is present at roughly 110 molar, and our protein of interest, or our molecule of interest, can be present in millimolar or micromolar concentration. So, because of this difference in concentration of the sample and that of the water, what happens is that this water signal is therefore in orders of magnitude. So, this was shown in the lectures that if you consider that the water concentration to be 110 molar and your sample concentration to be 1 millimolar, then if we estimate the concentration of, or the or magnitude of proton concentration in the solvent compared to that of the sample, then we can see that it is like 1 lakh times stronger, like, right? 1.1 into 10 to the power 5 uh, times. Okay, so what will happen? So the peak of the proton of the water will be so high that it will suppress the signal that is coming from the sample, right? So this creates a dynamic range problem. So the strategy, what is the strategy? So the strategy is that we can reduce the solvent magnetization before or during the acquisition, so that the weaker sample signals can be observed. So because of such a high concentration of water compared to the sample, your water signal will be so high that it will suppress the signal of the proton signal that is coming from your sample. Okay, so there are various solvent suppression methods that can be applied. So the first one that was discussed in the lecture was the pre-saturation method. So what is done over here is that you what we do is we continuously irradiate the water resonance with a weak RF field before the actual NMR acquisition. So you can see it was explained in the lectures that you apply a soft RF pulse on the water, and this is applied continuously. So when you apply this soft RF pulse specifically on the water, what will happen? The population difference that is there, right? The population difference between the two energy levels, they will get saturated. What does that mean? It means that there will be equal population on in the upper energy level and the lower energy level, right? So as a result, because of this saturation, we will not get any signal from the, or the signal that was coming from the proton of the water will get suppressed, and we can get the signal from the sample. Okay, so that is what has been written here: a weak 90-degree selective RF pulse centered on the water resonance. Okay, so water usually has a resonance around 4.8 ppm. Okay, so if we select a frequency that can specifically excite this particular resonance, then or this particular frequency of the water. So we will select an RF pulse which is having a frequency that will specifically excite this 4.8 ppm signal of the water, right? And so as a result, there will be saturation, there will be no population difference, and now the normal RF pulse can be applied. right? Normal RF pulse can be applied and the FID can be acquired. Okay. So this was one of the method that was discussed. Next, that was method that was discovered was inversion recovery. Okay, so what is done in inversion recovery is that instead of continuously irradiating the solvent, we exploit a difference in the T1 relaxation times. So what will happen is that you have your sample and you have the water as well. So the T1 relaxation of the protons of the water are, if they are very different from the relaxation of the T1 relaxation of the protons of the water, then we can what we can do, we can apply this pulse sequence, which is 180 degree, tau 90 degree, and we can then collect an FID. So what will happen is that, so if you look at this figure, so when you apply a 180 degree X pulse, so if you apply this right hand thumb rule, then what will happen, if so if this is your Z axis, this is your say y-axis, this is our x-axis, and you have applied a 180 degree X pulse. So initially in the steady state, what will be there? All the magnetization, bulk magnetization or the magnetization in the steady state, net magnetization in the steady state will be oriented in the z direction at zeroth time, right? Now when you apply this 180 degree X pulse. So I've applied this 180 degree X pulse. So what will happen if you apply the right hand thumb rule? Then this entire magnetization will shift from the Z axis to the minus Z axis. Okay. So now this 180 degree X pulse that you have applied, that will not only shift the magnetization of the water proton from Z axis to minus Z axis, but it will also shift the magnetization of the sample. So if you have the sample, so for example, this is your sample magnetization. So the sample magnetization will also get will move to the minus Z axis, right? And now then you are allowing a recovery time of tau. So in this recovery time, what will happen? This both the sample magnetization and the proton magnetization, they will start to precess and they will decay. They will start to decay, and then after that, you are again applying a. Now what the trick over here, the trick over here is that this you have to play around with this tau time. So you have to play around with this tau time in a way that this time, this recovery time that you are providing, it will be such that the water signal, water proton, the proton of the water comes to zero. Okay. So within in this tau recovery, water sample magnetization. So at a particular after a particular time, this magnetization of the water will come to a attain a value zero. So at that time when you will so after that time, but because your relaxation rate, the T1 relaxation of the sample is different from the water, your sample has not has not attained a zero value, but your water has attained a zero value. So now what will happen? Yeah, because your your water has come to a zero value, when you apply that the next 90-degree RF pulse, only you will get a signal from the sample and not from the water. Okay, so that is the trick. You have to play around with this tau time period. So it should be such that your T1 relaxation of the water comes to a zero value, so that when you apply the next 90-degree RF pulse, only your sample signal gets excited, while this will because this has become so. You if you see this, it was explained in the lectures as well. So your red colored magnetization is that of your water, and your green color, the arrow which is in green color, that is of the sample. So after this tau T1 recovery, what will happen? You see here that it has been adjusted in such a way that your water signal has become zero, but your sample has because maybe the T1 relaxation of the sample is less. it has been able to recover faster and come to a positive z axis, or somewhere between the z axis and x axis. Now you are applying the, so the main point over here is that you have to remember that the water and the sample should have different T1 values. If your water and sample have different T1 values, then only you can apply this method for water suppression. So if the difference in T1 is not very large, then sample and signal both will be attenuated. Okay. So this is the important point, that your T1 should be different between the sample and the solvent. So that is the important point, that choose tau so that the solvent magnetization passes through zero while the sample magnetization remains non-zero. Okay, so we want the tau value to be such that the solvent magnetization becomes zero, but the sample magnetization remains non-zero, so that when the next 90-degree RF pulse is applied, there will be it will shift to the transverse plane magnetization, and then once it will recover, we can record the FID. Another technique is the jump and return pulse sequence. So in jump and return, pulse sequences are also a method used for solvent signal suppression. So here, what you're, so the in your inversion recovery method, you were applying a 90-degree X pulse, 180-degree X pulse. So your 180-degree X pulse was causing the Z magnetization to move to the minus z axis. Then you were allowing a recovery of tau, and then you were allowing again providing a 90-degree X pulse, and then you were recording the FID. But in this case, what you are doing, you are applying a 90-degree X pulse followed by a recovery period of tau, and then a 90-degree minus X pulse. Okay, so here the time points are indicated in this figure, 1, 2, 3, 4, and how the magnetization is changing at different time points, that has been shown in this vector diagram. So so initially at time 0, what is happening? So both your solvent magnetization, or the proton of the solvent and the proton of the sample, both are oriented in the positive z axis. Now you have applied a 90-degree X pulse. So when you apply this 90-degree X pulse, what will happen? Now it will move to the, so if you apply this one right hand thumb rule, your magnetization will move to the minus y axis, right? So both the magnetization of the solvent and that of the sample has moved to the minus y axis. Now you are again applying a recovery of time tau. Now both of these, the frequency of your sample and frequency uh, of the water are, they are different, so they will now start decaying at different rates. Now again you are applying a 90-degree minus X pulse. So when you are applying this 90-degree minus X pulse, what is happening? Your water is again moving to the, will again move to the z axis, right? It will move to the positive z axis, but your sample will remain in this transverse plane. Okay, so as a result, you can see that there was a jump, and then it again returned to its original position. So that is, it is a jump and return pulse sequence. So if the excitation is to be maximized at a frequency nu max away from the offset, then tau is set equal to 1/4 nu max. So let's discuss the step one by one. So what is happening is the jump return suppresses water by making the water magnetization jump back to the z-axis. So as we saw in the previous slide, that what is happening, that when we are applying that 90-degree minus x pulse, the water magnetization is it will move back to the z-axis, while allowing nearby off-resonance sample magnetization to remain in the transverse plane and be detected. Okay, so your sample magnetization is remaining in the transverse plane, while your solvent magnetization is moving back to the z-axis, and hence you can detect the FID in the transverse plane. So what is happening to jump? What is why we are calling it jump? So the first 90-degree pulse that we are applying is causing the pulse, or is causing the magnetization to move into the transverse plane, and then the second 90-degree pulse, that is 90-degree minus X pulse that we are applying, it is causing the It is bringing the selected magnetization back towards the z-axis. So here, what is here, another important point is that the carrier is placed exactly on the water resonance. So because the carrier is placed exactly on the water's resonance, so now you can consider that you are sitting on the water uh, magnetization. So as a result, when you are applying the 90-degree minus x pulse, your water magnetization will uh, suppose so it will move back to the minus z axis. Okay, so suppose the water resonance is at 4.7 ppm, and we set the transmitter or carrier frequency to the water frequency. So placing a carrier on the water resonance means what? We are setting the transmitter or carrier frequency to that frequency of the water, that is 4.7 ppm. Therefore, in the rotating frame, what will happen? This new water minus new carrier equal to 0. So water is on resonance. If another proton has frequency nu I, then it will be delta nu I equal to nu I minus nu water. Therefore, the sample proton is off resonance relative to the carrier. Thus, water does not precess relative to the rotating frame. Okay, so here you can see that here the carrier has been placed on water, so the water is not precessing, but your sample will precess because it is in off resonance. Okay, so thus the water will not precess relative to the rotating frame, whereas the other resonances continues to precess. So that is why when you are applying the next 90-degree minus x pulse, your water will move now to the z-axis, while your sample will you will get the signal from the sample because it is staying in the transverse plane and it can be detected. So what should be the tau value in this case? So for maximum for maximum signal, what has to be considered, or what has to be taken care of, is that your tau value. So when you are so basically we wanted to rotate it by approximately 90 degree so that the second pulse produces a maximum transverse component, this theta. So basically this theta that we are talking about. So we have to set the tau value in a way that this within in this time period tau, this theta, if it is 90 degree, if we set the tau value in such a way that this theta becomes 90 degree, then when the next RF pulse is applied, then we will get only the signal from the sample, right? So that is why, so theta is basically what? Theta is equal to delta omega tau, right? Okay, so now we want that this theta should be pi by 2. Okay, so if we convert this omega into this radian per second, so it will be 2 pi times tau. Okay, I think I got disconnected. Yeah, but the important concept over here is that you have to set the time period such that it is having a value 1 by 4 into the offset frequency. Okay, so now try to answer this question in a jump return sequence for water suppression to excite a spectral region of 2000 hertz away from water. The value of tau in milliseconds should be. So in this question, what has been given is that it is given that this if this is your water, so if this is your water signal, okay, and your carrier is placed on water, so your sample signal is at a distance, it is 2000 hertz, it is 2000 hertz away from water. So the value of tau in milliseconds should be, so just now we discussed that tau, you have to, for the desired signal, the tau should be 1 by 4 times this delta nu. Okay, so that will be 1 by 4 into 2000, so that will be 1 by 8000. So if you divide this, you will get a value, that is option number B. 1 by 0.125 millisecond. Okay. So yeah, basically, if your omega is in radian per second, then you have to actually multiply it by 2 pi into the frequency delta nu to convert the radian per second into hertz. Okay. So that is what it was done over here as well. So your delta omega was converted into hertz by multiplying this 2 pi into the offset frequency 2 pi nu delta. No, I'm not able to. 2 pi into delta nu tau, and that should be equal to pi by 2. So from here you can derive this expression tau equal to 1 by 4 delta nu. Okay. Okay, so now let's quickly revise the concept of spin echo that was explained in the lecture. So it is an extension of one pulse FT NMR. So what is the pulse sequence for a spin echo? So the pulse sequence is 90-degree x tau, 180-degree x, and then tau. And after that tau time period, you are collecting the FID. Okay. So what is how? So we will understand one by one that what is happening at these different time points that are labeled as 1, 2, 3, 4, and 5. Sorry, I forgot to share the screen, I think. So we were discussing this question, and we discussed that we will keep the tau value such that it is 1 by 4 times of this offset frequency. Okay. 1 by 4 times of this offset frequency. So here the offset frequency has been given as 2000 hertz. So basically you have to multiply this 2000 into 4, and then when you solve this you will get the value 1.25 millisecond. 1.25 millisecond. Okay, so then we started discussing about spin echo. So the pulse sequence of a spin echo is 90-degree x tau, 180-degree x tau, and then we collect the FID. So here what is done is, so it was this was explained in the lectures as well. So first of all, what is happening? So initially at time t equal to 0, your magnetization is oriented in the z-axis. Uh, so this is at time point 1. Then you are applying a 90-degree x pulse. So once you have applied this 90-degree x pulse, your magnetization, what will happen? It will move to the y-axis or the negative y-axis, whatever you can say that it will move to the y-axis. Now you are allowing a recovery of tau time period. So now in this tau time period, what will happen? Your magnetization will start decaying, and it will in the transverse plane. And suppose it has moved to this position. It has moved to this position by an angle theta equal to omega I tau. Okay. So theta equal to omega I tau. Then what you are doing? You are applying the after this point you are applying the 180-degree Y pulse. So once you are applying this 180-degree Y pulse, what will happen is that your this magnetization will now this magnetization will move. So if you break it up into components x and y, you can understand that this y this magnetization will move in the xy plane, and then after this tau time period, it will again get refocused. Okay, it will again get refocused. So this tau time period is allowing the signal to refocus, and so there are two things that are happening in a spin echo. First is a dephasing that is happening, and after you apply this next pulse, 180-degree pulse, it will again 180-degree Y pulse. Once you are applying this 180-degree Y pulse, it will again be refocused to the it will again be refocused in the y plane. Okay. So yeah, so what is happening is this 90-degree pulse tips the net magnetization into the transverse plane. So here you can see it has both the sample. So here we are considering two the frequencies of two nuclei, and you can see that all. So once this 90-degree pulse is applied, it will come to the negative y-axis, and they will start precessing at the Larmor frequency. Now over the time tau, the spin begins to dephase, so both they will start to dephase. So that is what I was explaining. So there is a dephasing and then there is a refocusing. Okay, so they will begin to dephase, and after a delay tau, again a 180-degree pulse is applied. So now when this 180-degree pulse is applied, this 180-degree x pulse is applied, so these will interchange, right? So this demagnetization, so their orientation will change. Now then you are again, and then when you are applying this tau time period, so after the delay tau, a 180-degree pulse is applied. The pulse inverts the spins, flipping them about the x-axis. So your A will move to B and B will move to A. Okay, so about the x-axis they will be flipped, and then a rephasing will happen. So after the 180-degree pulse, the spins continue to precess, but now the faster spins catch up with the slower spins, so that at time 2 tau, so another delay tau, the spins rephase, resulting in the formation of a spin echo or a revival of the net transverse magnetization. So when you are applying the first 90-degree X pulse, there was a they will tip off, and then they will start precessing at their own Larmor frequency, which is what we are calling dephasing. Now after that, when you are again applying this 180-degree X pulse, they will interchange. The flipping will take place, and they will, after a recovery period of tau, they will refocus, and there will be revival of the net transverse magnetization. Okay. So basically, there is refocusing of the chemical shift. So when the two nuclei are not coupled, when the two nuclei are not coupled, there will be refocusing of the chemical shifts. Okay. But if we consider a case of a coupled spin system, so if we consider a case of coupled spin system, AX system, so a coupled spin system will have four energy levels, right? So your if it is coupled, then they will split into doublets, right? They will split into doublets. So why does this doublet come? We had understood in the lectures as well, and we had gone through these concepts in week 2 as well. So we can see that there can be four different energy states, right? Alpha A. So basically, there can be four different energy states: alpha A, alpha X, beta A, beta X. So there can be one transition. So the A1 transition would mean that this alpha, the spin states would move to beta A. This will remain as alpha X, and then this alpha A, beta X. Okay. So this is your A1. This is your A1, and this is your A2. A1 means what? Your alpha A will move to beta A, and here your and your X will remain in the alpha state. And if your X is remaining in the beta state and your alpha state is moving to beta state, then that is A2. So that is why these are the two peaks, A1, A2. Similarly for X, if we consider, then if your alpha X is moving to beta X, that is X1. And if your A nuclei is in the beta state, and if you're again here, if your a nuclei is in the alpha state and your X nuclei is more transitioning from the alpha state to the beta state, so that is why you are getting X1, X2. So what is happening if in case of coupled spin system is that once you are applying this 90-degree X pulse, so your magnetization will move to the y-axis. Now after a time period tau, they will start precessing at their own Larmor frequency. Now when you are when then again you are applying the 180-degree X pulse. So when you have applied the 180-degree Y pulse, 180-degree one Y pulse. So as a result, what will happen? Your there the spins will be flipped, right? Your your A will come to and your A will come to. Now, so here the catch is that you are because now you have applied this. So the important point over here is that you have applied the 90-degree X pulse on the X nuclei. You have applied the 90-degree pulse on the X nuclei. So that is why they have moved to this. They have come to the transverse plane and now they have started precessing. Now we are applying the 180-degree pulse on the. You are applying the 180-degree pulse on the X nuclei. So when you are applying the 180-degree pulse on the X nuclei, what will happen is that they will not get refocused, right? The two will not be refocused and they will again. They will the chemical shifts are not refocused for couple spins. So this is the important point. So the spin echo does not refocus coupling evolution. So the two are not refocused. So after this tau time period, you can see that A1 has moved to some point and A2 has moved to another uh, at a different position. Okay. There's some of the important points that were discussed in the lecture. That is that in case of a spin echo, the chemical shifts are refocused if it is not a coupled system, okay, or the field inhomogeneities are refocused because this chemical shifts arises because of this, or we can consider this chemical shift to be individual, as having individual. Each of the spin are having a magnetic field. So these field inhomogeneities are refocused. Chemical evolution is not refocused, or coupling evolution is not refocused. So if it is a coupled, if the two nuclei are coupled, then they will not be refocused. That is the case of the AX system that we discussed. But the relaxation will continue to happen during this time period. So this Pinnacle sequence is very good technique for determining the transverse relaxation, or the T2 relaxation rate. So it will relax by following this order e to the power minus 2 tau by T2. Okay, and from the transverse relaxation, we also get the line width. So if we want to determine the transverse relaxation of the nuclei, then we can go for the spin echo sequence. So that is what has been explained here. So in case of a weakly coupled AX spin system, you are applying the 90-degree X pulse. So once this 90-degree X pulse is applied, your magnetization has tipped to the y-axis. Now you are allowing a recovery of tau time period. So in this tau time period, they will this A1 and A2 will start to precess at their own frequency. But now you are applying the 180-degree pulse on the A nuclei. Okay. So this as a result of that, what will happen? This will be flipped. Okay. This will be flipped, A1 and A2, and the X nuclei. So you are applying 180-degree on both the A nuclei and the X nuclei, and but within in this time period tau, they will not be refocused. So after the first 90 pulse, the magnetization vectors corresponding to the transitions A1 and A2 of spin A are along the negative y-axis, right? So during the next tau period, they precess with different frequencies in the transverse planes and D phase. So the angle theta between the two vectors is given by 2 pi j tau, okay, or omega tau, or we can say that 2 pi j tau. So because now they are coupled, so that is why this coupling constant term is coming, AX system. So they are having a coupling constant of j. So that is why 2 pi j tau. So during the next tau period, the two transitions continue to dephase further, and at the end of the 2 tau, the angle between them will be 4 pi j tau. So the echo amplitude in the spin echo experiment is proportional to the e to the power minus t 2 tau by t2. Okay, thus fitting the echo amplitude to the data obtained. So the echo amplitude is that after that 90-degree x tau 180-degree y pulse, the FID that you are collecting, that is your echo amplitude, and your echo amplitude is proportional to e to the power minus 2 tau by T2. Okay, so thus fitting the echo amplitude to the data obtained for different values of tau allows the measurement of T2 relaxation time. So that is what I was trying to explain, that this spin echo pulse sequence is very useful for measurement of T2 relaxation times, tau values, and then from there you can calculate, measure the The precise refocusing of the signal in the spin echo experiment is dependent on each nucleus remaining in the constant magnetic field during the time 2 tau. If, however, there is molecular diffusion during this time between regions of different field strength because of field inhomogeneities, then the echo amplitude will be modified and we do not get the true value of T2. So here what they're explaining is that if there is field inhomogeneity, so in case of field inhomogeneity, there will be, because of this field homogeneity, the echo amplitude can get modified. Okay, that is e to the power. So this amplitude that was following this relaxation rate of e to the power minus 2 tau by T2, that will get modified if there is inhomogeneities in the magnetic field. Okay, and therefore we will not get the value of T2. So this is a very simple question that was asked in the assignment. So the spin echo pulse sequence will be what? It will be 180 tau 90, and then you are, no, this is not the. So first you will apply the 90-degree tau and then 180-degree. So which option? So this option is incorrect. So first you are applying a 90-degree X pulse, then you are allowing a time period of tau, 180 tau. So answer is option B. Option B. Okay. Hmm. The spin echo refocuses what? So just now we learned that what will it refocus? It will refocus the chemical shifts. If it will refocus the chemical shift, but if they are coupled, in case of coupled spin, the chemical shifts will not be refocused. So answer is option A. It will refocus all chemical shifts. Okay, so now try to answer this question. In a spin echo experiment on a coupled two spin system AX with coupling constant J, the phase difference between the two components of the doublet at the time of echo. So at the time of echo, just now we discussed this concept, right? It will be 4 pi J tau. Okay, so first it will move by, so when you are applying the first 90-degree expulse, and you are allowing a time period of tau, they will move by an angle 2 pi J tau. But after the next after that 180-degree pulse, next 180-degree pulse, they will move by an angle 4 pi J tau. Okay, at the end of the, because your tau has become 2 tau, so it will be this theta angle will become 4 pi J tau. So answer is 4 pi J tau. Okay, this explanation is wrong. It will be 4 pi J tau. Okay. So this is a two spin system, right? AX with coupling constant. So this is a case of a coupled spin system. Had it not been a coupled spin system, then it could be 2 pi J tau. But if it is a coupled spin system, it will become, so the in case of a coupled system, it is getting refocused, right? So phase difference, there is no phase difference because the chemical shifts are getting refocused. But in case of a coupled system, the phase difference will be 4 pi J tau. So the echo amplitude in a spin echo experiment decreases due to what? So just now we discussed. So if there is translational diffusion in an inhomogeneous field, then it can get decreased. Okay, the answer is option C. So because your chemical shifts are getting refocused, your inhomogeneity, field inhomogeneity are also getting refocused. But if even in that case, if the echo amplitude decreases, Even then, if the echo amplitude is decreasing, it means that there is some field inhomogeneity, or there is some translational diffusion in an inhomogeneous field. So in a spin echo, 90 degree tau, 180-degree tau acquired, we are acquiring the signal. The 180-degree pulse defocuses dephasing caused by the static magnetic field inhomogeneity. Okay. However, if molecules diffuse through an inhomogeneous magnetic field, they will move to regions with different magnetic fields during echo period. So their accumulated phase therefore cannot be perfectly refocused by the 180-degree pulse. Okay. So answer is option C. Now, in this Pinnacle pulse sequence, that another concept that was discussed was the water gate for water suppression. So this sequence, why it was discussed, because it is a modification of the spin echo pulse sequence only. So here, what is done? The sequence is designed so that the sample resonances experience a normal spin echo and a refocused, whereas water experiences essentially no net refocusing pulse and therefore remains dephased. Okay, so what we are trying to do over here is that we want the water signals to remain dephased, but the sample signal should get refocused. So water gate stands for water suppression by gradient tailored excitation. So here it was explained that you are applying first a 90-degree X pulse, and then you are applying selective pulses, hard pulse on the water signal. So you are applying a 90-degree minus X pulse and a 90-degree plus X pulse. And then, so you have here, you have applied selective RF pulses on the uh, 90-degree minus X and 90-degree plus X pulse, along with this 180-degree X pulse on the water. And also here, another thing that is done is that you apply field gradients. Okay, we apply field gradients are applied, so that what will happen, what do you mean, what do we mean by field gradient is that along this axis there is a gradient in the magnetic field. So along the magnetic field, at every point there will be an increase by this factor gz. So h naught plus gz, then h naught plus 2 gz. Okay, so as a result, what will happen? So the idea is that we want this water signals, water to remain dephased while the sample signal should get refocused. Okay, so that is what is explained here. So the first 90-degree pulse puts magnetization in the transverse plane, right? Because it is a 90-degree X pulse, it will put the magnetization in the transverse plane. Then they are for that is followed by 90-degree minus X, followed by 180-degree X, followed by another 90-degree minus X. So these next two pulses are soft or selective pulses which are centered on the water resonance. Okay, so first we are applying a 90-degree X pulse, followed by a 90-degree minus X pulse. These are soft pulses. 180-degree X pulse, then again a 90-degree minus X pulse. So these 90-degree, these are centered on the water resonance. So soft pulses act specifically around the water resonance, whereas the hard, so this is the hard pulse. 180-degree pulse acts on essentially all spins. So for water, what happens? The sequence of relevant pulses is effectively 90-degree minus X, 180-degree X, and 90-degree minus X. So the two 90-degree pulses will combine to give 180 minus X, and therefore water effectively experiences zero net rotation. Okay, the sample, so this will experience a zero net rotation. The sample resonance are far away from water, so that the soft selective pulses will not affect the sample signals or the sample resonance. Therefore, from the sample's perspective, the sequence is approximately 180-degree X. So the sample is experiencing RF pulse of first it experienced 90-degree X pulse and then a 180-degree X pulse. But because we have applied on the way we have applied selective 90-degree minus X pulses on the water resonances, this water will not shift. Okay, it will not be it will experience 0 degree net rotation. Therefore, the sample magnetization will get refocused once this 180-degree refocusing pulse is applied. And that is why what is done, this water gate are the selective soft 90-degree minus X pulse that is directly connected to the spin echo. Okay. So what was the purpose of this field gradient then? So the purpose of this field gradient was that it makes the dephasing much stronger and more controlled. So without a gradient, this water may dephase only because of chemical shift evolution, field inhomogeneity, and relaxation. But with a gradient, what we are doing, we are applying a gradient of delta Bz, and therefore omega z will be, we can say that it is gamma g, this particular factor. This gives us control spatial phase encoding or dephasing. Then the pulse sequence can decide whether that dephasing is refocused. That means the sample will survive or not refocused. Okay. Refocus means that sample dephasing will cause the sample signals to get refocused, while the water signal will not be refocused and it will disappear. Okay. Okay. See, so basically we want this water signal to dephase. Dephase. So we are applying that particular gradient, field gradients. Okay. So answer this question. This is again a simple question based on what we have discussed. So in the Watergate scheme for water suppression, what we are doing, option is employs spin echo sequence along with the selective pulse on water. The field gradients have no effects on water signal. The sample signals are dephased. Both the water and sample signals are dephased. So answer is option A, right? We are employing spin echo sequence along with the selective pulse on water, right? The field gradients will have effects on water signal because we want the water signal to remain dephased, and the sample signals are dephased. No, it is not true. It will refocus after the dephasing. It will refocus. Both the water and sample signals are dephased. This is also incorrect because only the water signals are dephased. So guys, the basic idea, what is the basic idea of this Watergate scheme for water suppression? So it the basic idea is that this 90-degree pulse will first, it will what? It will put both water and sample magnetization into the transverse plane. Then the magnetization will be allowed to dephase. Then us we are applying a selective pulse centered on water resonance that is combined with a broadband 180-degree pulse. So for the sample resonance, this selective pulse that has been applied on water, that will not affect the sample resonance. Okay, this sample water pulse have little effect, so they will only experience this 180-degree refocusing pulse. But for water, the combination of the selective pulses and along with that 180-degree pulse, because this 180-degree hard pulse means that it is applied on both water and the sample. So it will give essentially no net refocusing. So it will not allow the water signal to refocus, and this magnetic field gradients deliberately it will dephase the magnetization. Thus the sample magnetization is refocused and produces a signal, whereas water remains dephased and is suppressed. This is the important point. Water will remain dephased and it will get suppressed while the sample magnetization will defocus. The field gradients have no effects on water signal. This is incorrect option because as we had discussed that these gradients are important because they deliberately introduce phase dephasing or phase dispersion. So water is prevented from being refocused. So this dephasing helps suppress the water signal. The sample signals are dephased. This is incorrect, not as the final outcome, right? As the final at what is the final outcome? The final outcome is that the sample signals will be refocused, right? Sample signals will be refocused. We initially dephase the sample signals too, but the spin echo refocusing mechanism brings the sample magnetization back into phase. Okay, so for the sample, there is first dephasing, then refocusing, and then the signal is retained. So the option D is also, C is incorrect. Option D is also incorrect because we know that initially both will be dephased by gradients, but that is not the final result. The sample gets refocused and the water remains dephased. Okay, so now another concept that was discussed was the two-side exchange. So I hope these points are clear. So So NMR can also understand be from a solid state or from coil state to a heli state. So the those exchange. So what is the order of this exchange, or what is the time scale of this exchange? That type of experiments can be done in NMR by utilizing NMR. So if a nucleus exchanges between two chemically different, so that is how we this concept was discussed, two site exchange. So here we are considering that there is exchange between two states. Okay, for example, for proteins, you can consider that an unfolded domain or unfolded disordered region is getting converted to a helical conformation. Okay, in presence of a substrate, or it could be in absence of a substrate. But if we consider nucleus, then in nucleus also we can consider that there were examples that were provided in the lecture, like uh, tautomer that ketotouinol, or this proton transitioning between two tautomeric states. So if a nucleus exchanges between two chemically different environments, the appearance of its NMR signal depends on how fast that exchange occurs relative to the difference in resonance frequencies of the two environments. So, for example, if we consider a proton, this and we consider that this proton can exist in two different environments. Okay, uh, it can when it is so this is it can either exist in state A, or it can exist in state B. Or we can say that the proton spends some time in environment A and then moves to B, and it is again returning to A. So we want to determine that what is this exchange rate, that it is moving from an environment A to environment B. Now, because A and B are chemically different, the proton has different frequencies. They have different resonance frequencies. Omega A is the frequency of this proton in state A is not equal to the frequency in state B. Omega is not equal to omega B. So if there were no exchange, we would simply observe two separate NMR signals. So because they are in different chemical environments, so we would get two different peaks, right? For this A state, when the proton is in A, or they are not transitioning, it means that they will have two separate peaks. Okay, or these protons are staying in there in they are not transitioning. They're the two protons are staying in two different environments, so we are getting two different peaks basically. So we would simply observe two separate NMR signal. But if this protein is now continuously moving, then the spectrum starts changing, and the appearance of the spectrum depends on how rapidly the exchange occurs. So what is the rate of exchange between these two states, that can be determined from how these two NMR signals or proton signals are exchanging. So this has been beautifully explained in this figure, right? So this was explained in the lectures also. So when the exchange rate is very slow, that is k equal to 10 hertz, you are getting two separate signals, right? Two separate signals. Now as the exchange rate is increasing, we can see that the peak height is decreasing, right? And now at a particular frequency, what is happening is that these two signals, the two proton signals, have merged, and this point was discussed as coalescence. Now and the peaks have become broader. Okay, so the peaks have merged. We can see that the peak intensities have dropped as the exchange rate is increasing. Now at a particular frequency, these the two peaks will merge or coalesce, and at even higher frequencies, these will merge to give a single NMR peak or single proton peak, um, of and this peak will be present. So if we consider that the lifetime of the nuclei in state A is equal to the lifetime of the nuclei in state B, then it will, or if we consider that the population of the nuclei in state A and in the environment B are equal, then this signal that will be exactly. So this is a simulation study, right? So in this simulation study, what it has been shown is that it will exactly come midway between the two frequencies, initial frequencies. Okay. Okay, so let's understand one by one. So here we are considering that A is transitioning, this proton in state A is transitioning to state B, and that is given by this rate constant K1. Or it can also transition from state B to A, that is given by this rate constant K minus 1. So K1 is the rate of transition from A state to B state, and K minus 1 is the reverse of that. So the overall exchange rate can be defined as what? It can be defined as K exchange will be K plus 1 plus K minus 1. or K1 plus K minus 1. Now another exchange rate can be defined actually by two parameters. So first we have to also consider population. So the overall exchange rate will depend on the population. Uh, that is PAPB is the population of state A, and population of the protons in state B is PB. So how much, and also it will be defined by the lifetime of the nuclei in state A and state B. Okay. So so one is this population and another is lifetime. Okay, so the lifetime is actually inversely proportional to the exchange rate. So if the molecule stays in state A for an average time tau A, then we can write that this K1 is equal to 1 by tau A. Similarly, we can write that if this molecule exists in state B for a lifetime of tau B, or for an average time of tau B, then we can write it as K minus 1 equal to 1 by tau B. So what we are considering over here, so because we just now learned that K exchange equal to K1 plus K minus 1, and A to B is what? A to B is K1, rate constant is K1, and B to A transition is given by this rate constant K minus 1. So we can write this K1 can be now replaced by 1 by tau A plus 1 by tau B. Okay, so and if we consider that this is equal, or equal population case, for equal population case, we can write that this is tau A is equal to tau B equal to 2 tau, equal to 2 tau. Okay, is equal to 2 tau. So that is an equal. So in this case, an equal population case has been considered for this simulation study. Okay. So this coalescence condition was also discussed. So for equal population two-site exchange, what happens is that tau delta omega is root 2. Okay, this condition. So at what condition you will get this coalescence? So that is given by this this one, tau tw equal to omega. Tau del omega is equal to root 2. Okay. So at what frequency? At what frequency the two signals will merge? That will be 1.414. So we can also derive this equation as well. So because K exchange is equal to 1 by tau, now we can write in place of tau, we can write this root 2 by omega, right? We can replace this, and K exchange equal to delta omega by root 2. So we can actually derive that at what exchange rate the two peaks will coalesce. So we can derive it from this consideration that at condition when tau del omega is equal to 1.414, the two peaks will coalesce, and from here we can actually derive that what should be the K exchange rate in such a case. So the K exchange rate can be given by 2 pi delta nu divided by root 2. So basically, from all this, what has to be understood is that if the exchange is slow, it would mean that this K exchange is much less than delta omega. Okay, so this is the, so here you can see here, this is the slow exchange. So in case of slow exchange, so in case of slow exchange, this K exchange is much less than delta omega, right? That is the condition. K exchange is much less than delta omega, or the separation of the peak. If the exchange rate is much less than the separation of the two peaks, then as a result A and B are separate signals. Then we will get two sharp peaks. Now intermediate case would be what? If the exchange rate is equal, or it is roughly equal to the difference in the frequencies, then that is the case of coalescence or broadening, exchange occurring on NMR time scale. Now if the exchange rate is very fast, if it is very fast, then we will only get a single sharp peak. So that is a population weighted average. Okay. So where does fast exchange peak appear? So just now we discussed. So we can actually We can actually derive it from this equation. Is that if you're the observed, so the for in case of fast exchange, we will get a single NMR peak. Just now we discussed. So for slow exchange, we will get. So when the K exchange is much smaller compared to the separation of the peak, then it is a slow exchange. If the K exchange is much greater than the separation of the peak, then that is a fast exchange. So in case of fast exchange, we will get a single peak of both the proton in the two different environments. So the omega observed will be Pa, population of the nuclei in environment A times omega A, plus Pb into omega b. So now for equal population, we are considering that 50% of the, or it is a probability, if we consider that 50% of the nuclei are in the A state and 50% are in the B state. So that is a Pa equal to Pb equal to zero point 0.5. So we will get the observed frequency will be exactly half of the frequency in the frequency of the proton in the A state and frequency of the proton in the B state. So that will be exactly half. Therefore, the peak will appear exactly halfway between the two original resonances. So originally, when there was slow exchange, if this is your omega A, this is your omega B, then so this was the original resonances. So in at fast exchange, and in case of fast exchange, this will exactly appear midway. It will appear midway between the. So it will be this omega observed. This omega observed will be omega A plus omega B by 2. Okay, it will appear exactly halfway if the and here one thing that we are that has been considered, that has been uh, the uh, Hmm. Has been considered is that we are considering that the population of the proton in state A and state B, or environment A and environment B, are equal. Only in that case, your observed frequency in case of in the fast exchange state will appear midway between the two original frequencies. But if your populations are different in the two state, then the peak will be shifted towards the one which is more highly populated. Okay, which is more highly populated. So for example, if this is like this, then in the fast exchange peak, where will it appear? It will be more inclined towards the one which is more highly populated. This is the fast exchange peak, and this is the original peak, omega A and omega B, and this is the observed NMR signal, proton signal at the fast exchange condition. So a proton exchange between two sites A and B. So there is a proton which exchanges between two sites A and B. The proton chemical shift difference between the two sites is 1000 hertz. The two lines will get broadened. So if the proton chemical shift difference between the two sites is 1000 hertz, the two lines will get broadened at what? So just now we discussed the conditions, right? If omega, if K exchange is much less than delta omega, then it is what? It is slow exchange. The slow exchange. If K exchange is almost equal to delta omega, then it is intermediate exchange. Intermediate exchange, or we are calling it as the coalescence condition or coalescence, right? And if your K exchange is much greater than delta omega, or the proton chemical shift between the two sides, right? That is what is delta omega. Okay, then it is a fast exchange, condition of fast exchange. Okay, so two lines will get broadened at what? When it is 1000 hertz, exchange rate is closer to 1000 hertz. So this is the second case, right? So this question is asking you about the second case. That is why your answer is option number C. So if your delta nu is equal to 1000 hertz, and you want the peak to get broadened. You and you are observing that the two lines are getting broadened. So at what condition that will take place? So that will take place at a condition when the exchange rate is almost equal to the frequency or the chemical shift difference between the two sides. Okay. The exchange occurs on a time scale comparable to the difference in the resonance frequencies. This is the intermediate exchange regime where the two NMR signals undergo maximum line broadening and eventually merge at coalescence. So here K exchange, when it is equal to the difference in the resonance frequency or difference in the chemical shift of the two protons at the two different of the protons at two different sides, then it will give significant broadening. Okay, so this is the concept, this one, right? Condition. So if it is less than, we will get two relatively sharp separate peaks. When it is fast exchange, we will get only one relative sharp average peak. So now coming to nuclear Overhauser effect. So this one's again discussed in the lecture. So what is nuclear Overhauser effect? So this is again a this is transitioning to polarization transfer methods. Okay, so this is the polarization transfer method. So in polarization transfer, what is happening is basically the magnetization is transferred from one spin to another. So this is a type of polarization transfer phenomena, and NOE is a particularly useful tool for determination of structure by NMR. So by utilizing NMR, we can assign the peaks that we the peaks of the. So we will understand this in the later lectures. So it is an assignment tool. We can assign that what are the amino acids, what is the C alpha carbon, what is the uh, al- alpha hydrogen, what is the beta carbon. So using nuclear doing this NOE experiments, NMR experiments, we can assign the peaks, NMR peaks, and it is especially useful for structure determination of macromolecules such as proteins. So NOE is a phenomena. So let's understand this NOE in quickly revise the concept that was discussed in the lecture. So it is a phenomena in which perturbation of one nuclear spin can produce a change in intensity of another nearby nuclear spin through dipolar interactions. So this is very important. So we are dipolar interactions means we are considering here that the perturbation in one of the nuclei is affecting another nuclei through space. So this is the transfer of the magnetization transfer from one spin to another spin is taking place through space. So that is what is called as dipolar interaction. So perturbing a particular resonance by applying RF irradiation at its resonance frequency could be done through saturation, that is continuously irradiating spin s with radio frequency. So suppose we saturate proton s. So so if there are two protons, say there is a proton S and there is a proton I. Okay, there is a proton S and there is a proton I. Then if we perturb or if we saturate the signal of proton S, then will it affect or will it affect the signal of the proton I? So that is what is the idea of nuclear of this NOE. So if there is an interaction between S and I, or if the separation, basically the main concept of NOE is that the how close these protons are to each other. So if they are close to each other, then this dipolar interaction or this magnetization transfer or polarization transfer will take place more efficiently. Okay, so if there is an interaction between S and I, the perturbation can be transferred. The relevant interaction here is dipole-dipole interaction. So this is an important point. This is not through bonds. Through bonds is what we have learned in J coupling. So we have learned that the perturbation in one nuclei can affect the other nuclei through bonds. So that was J coupling. So we learned three bond coupling, two bond coupling, right? So three bond coupling, this carbon can perturbing this carbon can also affect the signal from of this carbon, the chemical shift of this carbon. So this was through bonds, but NOE we are considering dipolar interaction, or that is taking place through space. So two nearby proton magnetic moments can interact through space, and this is what is called as dipolar coupling. So this point is very important. So when two nearby proton magnetic moments interact through space, that is called magnetic dipolar coupling. So this is different from the scalar J coupling. So scalar J coupling is transmitted through chemical bonds. Now NOE can tell us which nuclei are close together in space, even if they are not directly connected by chemical bonds. Okay, so we can get the information through NOE experiments. We can get information on how closely the two protons are present in the molecule, or how far apart they are present. Okay. Magnetic moments are interacting through space. Okay. So how is the NOE detected? So here we are considering two irradiation. One is off resonance irradiation, and another is on resonance irradiation. So in off resonance irradiation, what are we doing? We are not perturbing the spin S. Instead, we apply the RF irradiation somewhere away from an actual resonance. This is called off resonance irradiation. This gives us a control spectrum I naught, where I naught is the equilibrium intensity of the observed spin I. So we want to study the perturbation in on spin S, or effect of perturbation on spin S, but we are not applying the signal on spin S. We are applying it at a different frequency, which is away from the frequency of the S spin. Okay, so we irradiate exactly also. And on resonance, what does on resonance irradiation means? So we irradiate exactly at the resonance of the spin S. So when we irradiate exactly at the resonance of spin S, what will happen? This S becomes perturbed or saturated. We record the spectrum again. So now the intensity of the spin will change to I. So when we are so first we are applying an off resonance irradiation. So the intensity that we are getting, that is an equilibrium intensity, or we are denoting it as I naught. I naught. Now we are applying the RF pulse exactly at that particular resonance frequency of the spin S. So that is the intensity change that has been observed is named as II. So the intensity of the spin will change to I. So we now calculate the difference of the perturbed spectrum minus the control spectrum, or the reverse, depending on the convention. So now if we calculate the difference between the two, then that is what is NOE. Okay, intensity of the perturbed spin minus the intensity of the control. So what will happen? Most signals that are unaffected will disappear in the different spectrum, right? Because if the signal in the unperturbed and the perturbed, they are the same, and when you calculate the difference between the two, then those signals will vanish, right? They will become zero. But the spins that have experienced a NOE will show a difference. So the difference spectrum can either show what? It can either show enhancement, or it can show a decrease in the affected signal. Okay, so whether on perturbation the signal has increased or whether it has decreased, and when we are subtracting, what is the difference that is coming, that will depend whether there is an enhancement or a decrease in the signal. So that is what. So here eta is means what? So we are calculating the NOE by perturbing the spin S, and we are calculating the intensity change. So it is the intensity of spin I after perturbing or saturating spin S. So we are calculating the intensity of spin I on perturbing the or saturating the spin S. So that is the intensity that we have obtained is I, and the equilibrium intensity of spin I in the control experiment is I naught. So your NOE will be what? I minus I naught by I naught. So NOE is useful for determining distances, because the dipolar interaction is strongly dependent on the distance between the two nuclei. So anyway, this is a very important point, is varies as the sixth power of the internuclear distance. Okay, internuclear distance. Now NOE will also depend on what? So these points are clear, right? So NOE all will depend on molecular tumbling, and so molecular tumbling is again controlled by the molecular size. So if a molecule has a large molecular size, so higher molecular size will molecules which are having a higher size will have slow tumbling. They will show slow tumbling, and if the molecular size is high, and if it is low, then they will have fast tumbling. Fast tumbling means fast relaxation rates as well. So that is the tumbling or the molecular motion is given, or it is characterized by the rotational correlation time. It is defined by this term tau c. Tau c, rotational correlation time. So tau c is a characteristic time for molecular reorientation or tumbling in solution. So you can see that for small molecule, your tau c is very less, 10 to the power minus 12 to 10 to the power minus 10. So they are tumbling very rapidly. Okay, and for large molecules, the rotational correlation time is in the range from 10 to the power minus 12 to 10 to the power minus 8, comparatively larger. So relaxation rate and NOE depend on the tau c. Okay, or on the rotational correlation time. So NOE depends on the internuclear distance. We understood that point, and also it will also depend on the molecule. So whether it is a large molecule, on the size of the molecule. If it is a large molecule, it will have slower tumbling rate, or the rotational correlation time will be less or high. It will be high, right? Large molecule will have higher rotational correlation time, and for small molecule, the rotational correlation time will be small, which means that it is tumbling very fast. Okay, so now two cases were discussed, right? So NOE was discussed for two cases. One was the for small molecules and another for large molecules. So for small molecules, what we learned just now, small molecules have very fast tumbling, or their tumbling motion. Okay, their fast tumbling motion. Fast tumbling motion means the rotational correlation time. This tau c value will be less. Okay, because they're in a fast tumbling motion. Okay, so in that case, the we are observing the NOE of in nuclei of the A nuclei by perturbing the X nuclei, right? So we have saturated A, and we are observing the intensity of the X nuclei. So this notation is important. So if it is written in this form, it means that we have perturbed the A nuclei. A nuclei has been perturbed, and we are observing the intensity signal of the X nuclei. So that will be given as half gamma A divided by gamma X. Okay, half gamma A divided by gamma X. What is your gamma? Gamma is basically your gyromagnetic ratio. Okay, is your gyromagnetic ratio of the nuclei A divided by gyromagnetic ratio of nuclei X. Okay, so A is what? A is your perturbed or irradiated spin, and X is the observed spin. So we have saturated the signal of A, and we are observing the intensity change in X. Okay, and gamma is the gyromagnetic ratio. So the magnitude and sign of NOE will depend on what? It will depend on the gyromagnetic ratio. So we learned that the gyromagnetic ratio of some nuclei are negative, like that of nitrogen 15, right? It will also depend on the molecular motion, correlation time, and relaxation processes. So all these factors will influence the NOE. So first internuclear distance we learned the rate of motion or the relaxation rate, or over the size of the molecule, or also depend on the size of the molecule, and also what is the gyromagnetic sign of the gyromagnetic ratio, whether it is positive, whether it is negative. So for small nuclei it will have, so that is what has been explained in the lectures as well. So NOE will depend on relaxation times, and relaxation times are in turn defined, or they are dependent on molecular motion of the macromolecule. So whether and the molecular motion is defined by the rotational correlation time. Okay, so for this is also known as steady state NOE. Steady state NOE. So eta A x means we have saturated the signal of A, or we have put up the signal A and we are observing the signal. We are recording the FID of the X nuclei. So that will be given by half gamma A by gamma X. So this is also called as extreme narrowing limit. So this is applicable for small molecules. Remember this half gamma A by gamma X will be applicable for small molecules. Okay, small molecules which have very high tumbling rate, or the rotational correlation time will be very small. Okay, so that is what, but it will not follow this NOE, this equation that has been provided. It will not be followed for large molecules. Okay, so for large molecules, the equation will follow this one. It will follow this equation eta. So we have saturated the signal A, and we are observing the change in the X nuclei. Okay, so that will be given at minus gamma A by gamma X. For large molecule, eta AX will be minus gamma A by gamma X. So this was explained in the lecture. So for a homonuclear system, what will happen? Homonuclear system, X will be equal to A. So as a result, what will happen when you are doing this? You will have gamma A by gamma X. So this will be minus gamma X by gamma, or if A is equal to X, then this minus gamma X by this will be minus 1. Okay, this will be minus 1. Okay, so for large molecules, so if you see this, so this graph is very important. So for large molecules, what will happen? So large molecules, we understood that large molecules have high tau c. So that is why how high tau c means what? High tau c means what? They are large molecules. So at large molecules, they will have a value minus 1. Okay, value minus 1. For small molecules, it will have a value zero point 0.5. Intermediate regime is 0, and large molecules will have minus 1 value as tau c increases. So as tau c increases, molecular tumbling becomes slower. Okay, molecular tumbling will become slower, and so the sign of NOE can provide information about molecular size or motion. So this is also an important point. So if your sign is negative, it means that it is a large molecule. It is a large molecule, and that is why its motion is very slow. Okay. So two things we discussed, that your NOE saturated the signal A. We are observing the intensity change in nuclei X. So for small molecule, it is half gamma A by gamma X. Okay, but for large molecules, it will be minus gamma A by gamma X. Okay. So what is transient NOE? So in transient NOE, what is done is that instead of continuously saturating spin A, instead of continuously saturating spin A, we are applying a selective 180-degree pulse. So when we are applying the selective 180-degree pulse, what will happen? This will invert the magnetization of one selected resonance. So here you can see that this is your intensity I naught, basically I naught, when you have not perturbed any of the nuclei. So this is your intensity, okay, of resonance, or of resonance irradiation. This is the signal that you are getting. Then what you have done, you have applied a selective inversion on this X by you have at a particular chemical shift, or at a particular frequency. So when you have applied this selective inversion pulse, what will happen? Your signal has inverted. It has inverted to the minus. It has become negative. So this inverts the magnetization of one selected resonance, and now because of this perturbation, now this perturbation will also influence the nuclei which are closer, the proton which are closer to, which are close to this particular nuclei. Okay, so there will be some shifts in the intensity of these nuclei as well. which are closer to the nuclei which has been perturbed. And now after that selective inversion pulse, you are allowing the system to evolve for a defined mixing time tau m. Okay, tau m. So magnetization in now in this this mixing time, this tau m is also called the mixing time. We will learn about mixing time in 2D NMR. In the lecture 4 we have seen also. So this in this mixing time, what will happen? The magnetization will be transferred from the perturbed spin to the nearby spins, and then again, what is a hard 90-degree pulse is applied, and then the spectrum is recorded. Or so a hard 90-degree pulse means what? All the nuclei will be perturbed. Okay, all the nuclei, the intensity of all the nuclei will be affected. Okay, selective means it's the soft pulse, means it will only perturb that particular nuclei. So this perturbed magnetization will relax after. So during this time, this mixing time, the perturbed magnetization relaxes back towards equilibrium, transfers magnetization to nearby spins through dipolar cross relaxation. Okay, so the intensity of the nearby resonances change. Okay, so during this mixing time, what will happen? The magnetization, this polarization transfer is taking place. That means the magnetization will transfer from the particular nuclei to the neighboring nuclei, which is close to the particular nuclei which has been perturbed, and this magnetization is transferred through cross relaxation. Okay, through space. So some as a result, what will happen? Some signals will relax, some signals will increase, or some may remain unchanged, and this will depending on what is the sign and efficiency of the nuclear Oberhauser effect. So in transient NOE, what we are doing, we are not saturating a particular nuclei by applying continuously. If we are not applying that RF pulse continuously on a particular nuclei and saturating its signal. Instead, what we are doing, we are applying a 180-degree selective inverse pulse, or selective 180-degree pulse that will what will it selective 180-degree pulse that will invert the magnetization of that particular selected resonance. Okay. So this is an important concept. So you have to understand that NOE, what is the relation of the NOE with the mixing time. Hmm. So this point is very important. So for small molecules, you can only measure the mixing time, or you can measure the NOE. Or you can measure the NOE when the mixing at when you keep the when the during the small mixing time. Okay. So if the mixing time is allowed to become longer, the magnetization progressively spreads through the network of coupled spins. So here in this figure, it was explained. So you are perturbing this particular nuclei, this particular proton, but all the protons which are present nearby to it, the magnetization will be transferred to those particular to all those different protons which are nearby to the proton which has been perturbed. So this is called spin diffusion. This is called spin diffusion. So, if the mixing time is kept very long, then what will happen? This spin diffusion will take place, or the magnetization will progressively spread through the network of coupled spins. So, all the protons which are closer to that perturbed proton, they will get the magnetization will get transferred to those protons. So this phenomena will be called spin diffusion, and spin diffusion is the progressive transfer of magnetization through a network of dipole-dipole coupled spins. So all the protons which are coupled to which are dipole-dipole coupled, or which are close to each other. So this what is then? So NOE should always be measured in the short mixing time regime. So region. So in this region, what will happen? The magnetization transfer is mainly between directly interacting on nearby spins. So if you keep the mixing time small, then in this small short mixing time regime, what is happening? The spin diffusion is not taking place. So the magnetization will only be transferred to the neighboring nuclei. Okay, to the neighboring nuclei. It will not be transferred to the network of the nuclei which are dipole-dipole coupled to each other. Okay, so the spin diffusion is minimal, right? So NOE intensity can be related to interproton distance. So we are hmm, this is interproton distance. arises reverses. Therefore, even a small change in distance can produce a large change in NOE intensity. So it varies as the sixth power of the interproton distance. So if there is a very small so even a small change in distance. So if the interproton distance is very small, even that can result in an enhancement of the NOE signal. So that was what was explained in the lecture as well. So you can calculate the interproton distance from the NOE intensity in this short mixing time regime. Short mixing time regime will be considered for, these are some of the very important points. Okay, short mixing time regime will be considered for calculating the interproton distance. Okay, so if you have to calculate the interproton distance, then you have to calculate the NOE in the short mixing time regime. So for short tau m, short mixing time, your dipolar coupling constant varies as the inversely varies inversely with the sixth power of the interproton distance. So basis of structure calculation is what the transfer is restricted to. So we in this short mixing time, what we are considering is that there is no spin diffusion. It will the magnetization will only be transferred to the neighboring nuclei. Okay, so enhanced signal intensity of less sensitive. So NOE, what is the advantage of NOE? It is enhancing the signal intensity of the less sensitive nuclei, and it is also helps us derive the structural parameters. So in NOE arises due to what? So we just now discussed that it is not due to J coupling. J coupling means the magnetization of um the that is taking place through chemical bond. Okay, but nuclear Oberhauser effect will always arise from dipole or dipolar interaction between two spins through space. When one spin is perturbed, magnetization can be transferred to the nearby spin through this dipolar interaction, resulting in a change in intensity. Answer is what? Dipolar coupling between two spins. Okay. Okay. Steady state proton NOE is what? So we just now learned that steady state proton NOE for large molecules will be what? For large molecules it will be NX A. It will be minus gamma A by gamma X for large molecules. This will be for large molecules. Steady state NOE. And for small molecules it will be what? It will be half gamma half gamma A by gamma X. Nice. For small molecules. So this is for steady state NOE. Okay. So answer is option B, negative in large molecules. Negative in large molecules. So it's not negative for small molecules. For small molecules, it is half gamma A by gamma X. So it is positive. It is positive in large molecules. It is B. So in an AX system, while saturating the A spin, the polarization gain I have. Okay, so we just now discussed AX system saturating the A spin, the polarization gain by steady state NOE will be what? So we have saturated the A and we are observing signal in X. Eta saturating the spin A. Okay, X. So we what? It is what? It is proportional to gamma A by gamma X. Half gamma A by gamma X. It is proportional, so that will depend. It is proportional to gamma A by gamma X. For small molecules, it will be half gamma A by gamma X, and for large molecule, it will be minus gamma A by gamma X. Okay. Estimation of distance between spin A and X by a transient NOE experiment will require what? Who can answer? So just now we discussed that if we want to calculate the interproton distance, then we have to calculate, or we have to determine the enhancement in the short mixing time regime. In the short mixing time regime, okay, because in the short mixing time regime there is no spin diffusion. Okay, we are conserving in this short mixing time, the dipolar or the transfer of magnetization will only take place to the neighboring proton, and it will not get diffused to the network of other protons. So now another concept that was discussed was the selective population inversion. So if we consider a two spin system AX, then for a two spin system we have, what do we have? We have four energy states, right? So four energy states. So as we discussed, alpha A, alpha X, and beta A, beta X. Then if we consider that this is remaining in X, this will be beta A, right? And if we consider that remaining as alpha A, this is beta X. So this is transition of the X nuclei, or the X spin state. A is remaining in the alpha state, and this is the transition from this is the transition of A nuclei, because it is transitioning from the A state to the B state, and the X nuclei is remaining. So this is X. This is X. Okay. So this is the transition that is happening for A1 nuclei, and the A2 peak that we get because of this transition. A1 peak that we get is because of this transition. So we consider here that this is delta plus delta. This is at a in a state that is minus delta plus delta. So here we have considered that the for X we have considered that it is having a frequency of capital delta, and this is having a frequency of delta, okay, small delta. So this is delta plus delta, this is minus delta plus delta, this is delta minus delta, and this is minus delta minus delta. Okay, so transition from this state to this state will be what? So this will be delta plus delta minus of minus delta plus delta, or minus delta. So this will be what? This will be 2 delta. Okay, so that is why for this one, for transition from here to here, you get 2 delta for A1 and 2 delta for A2. Similarly, if you subtract this from this for x1 if we consider, then delta plus delta minus delta minus minus will give you plus. So this will be 2 delta. And that is why for x1 and x2 you will get frequencies at 2 delta. 2 delta. Now what we are doing here, so we are considering that this delta is much greater than this small delta. Okay, so we have inverted this. We have inverted the we have applied a frequency which inverts the this A1 nuclei. So in that case, what will happen? This delta has become now minus. This delta has become minus delta plus delta, and this has become delta plus delta. So and this, but this one x1 we have not changed, so this one will remain as it is. So now what will happen? So for the X nuclei, for this A1 nuclei, what will now happen? Minus delta plus delta minus delta minus delta. So it has become minus 2 delta, right? Minus 2 delta. From 2 delta, it has become minus 2 delta. And this one, for this transition, it will become plus 2 delta. So now the two frequencies or the chemical shifts will be antiphase to each other. Okay, 2 delta and minus 2 delta. Similarly, for this one, for this X nuclei, we are considering that it is having a lower polarization. rate. Okay, so that is why it will be. And so here, after this inversion, selective population, you are selectively inverting the population. So from 2 delta, it has now become, it has gained a factor 2 delta, 2 capital delta, or 2 bigger delta. And this has become what? This has become minus 2 delta plus 2 delta. So these two signals are again different. The intensity of these two signals are different. So enhanced intensity for the X transition. So the less sensitive nuclei, has so from the selective population inversion, what we are getting is that the less sensitive, the polarization transferred from the more sensitive nuclei to the less sensitive nuclei has resulted in an enhancement of the signal of enhancement in the less sensitive nuclei. Okay. So magnetization or polarization is transferred from the highly polarized A spin to the less sensitive X spin. So the enhancement will depend on what? It will depend on the ratio of the gyromagnetic ratio of X and gamma of A. So therefore, this effect is especially useful for heteronuclear systems. Okay. So the highly polarized A is highly polarized. That is why we were denoting the it as delta, and the frequency as delta, and X was less sensitive, so we were denoting the frequency as this, by this sign. Okay. So enhancement, we can say after this selective inversion, there has been an enhancement of the less sensitive nuclei. So the advantages are that there is significant signal enhancement, and it is particularly useful for heteronuclear systems. The transfer polarization from a sensitive nucleus to a less sensitive nucleus is taking place. That is an advantage. Provides a route to enhance detection of insensitive nuclei, but another disadvantage is that we are getting both positive and negative signals, right? So the selective inversion is creating antiphase signals. So this is that you initially you had positive signal, but because of the selective inversions, you are now having both negative signal and positive signal, and that is what is called an antiphase magnetization or antiphase signal. So that is why we cannot decouple A and X. Another disadvantage is that we cannot decouple A and X, and selective inversion also requires long pulse. Long pulse means now we cannot apply a pulse of 10 microsecond. It has to be in millisecond, or in milliseconds. So selectivity becomes difficult in case of complex spectra. So this is just a very simple system of AX spin system, but for complex spin system, selective inversion will be more complicated. So this brings us to INEPT. So INEPT is what? So in INEPT basically circumvents the issue related to selective inversions. So the issues that were there, right? The issue is that we have to selectively apply the pulse on one of the nuclei that can be overcome, right? So in selective population inversion, the difficulty lies in obtaining a selective 180-degree pulse. So you have to give a selective 180-degree pulse that will specifically invert the A nuclei, right? The A nuclei, the frequencies of the A nuclei. But difficulty arises when the resolutions are poor or spectra are crowded. Okay, so if the spectra are crowded or for multi complex spectra, we can use the INEPT. So in INEPT, what we are doing is that we are applying. So here, if you consider, so this was discussed. So initially, you are having two delta, and this A1, which is having this is a more sensitive nuclei. This is having two delta. So after inversion, you are applying a selective inversion pulse on the A1 nuclei. So as a result, your A1 nuclei is getting is now they are getting enhanced. They are getting enhanced by two delta, and this is minus two delta. Okay, but the yeah, this is there is an antiphase signal that is coming, but the less sensitive nuclei is gaining there is an enhancement by two delta, right? Two delta and minus, and also these signals are not equal. But that's one of the signals is larger than the this negative signal, signal. So selectivity is a problem, and we are also getting positive and negative signals. So these are the two main disadvantages. So in INEP, what we are doing is that we are applying a 90-degree X pulse followed by tau 180-degree X pulse, tau and 90-degree Y pulse. So the SPI transfers polarization from a sensitive nucleus X to an insensitive nucleus, from a sensitive nuclei A to an insensitive nucleus X. But inept, what will it do? It will transfer polarization from sensitive nucleus A. It is also doing the same thing, but So sensitive nuclei means we can consider proton, and insensitive we can consider carbon 13 or nitrogen 15 because their gyromagnetic ratio are lower compared to proton. So insensitive nuclei enhancement by polarization transfer. So what we are doing is we are first applying this 90-degree S-pulse. So now we are no longer selectively exciting one of the nuclei. So first, what will happen when you are applying this 90-degree S-pulse? So both of these will be come to the transverse plane. Then they will start to precess with each other in this one in tau equal to 1 by 4j time period. Then after that, you apply a 180-degree pulse, 180-degree X pulse. So there will be flipping, right? A1 will become to come to A2, A2 will come to, and there will be flipping. So after that, you again apply this 180-degree X pulse. So they will, what will it do? Now they will move by tau equal to 1 by 4j. So this will, if this becomes 1 by 4j plus 1 by 4j, so this will become pi. This will become pi. So first it was pi by 2. This will 2 2 tau, right? 2 pi j into 2 by 4j basically. Okay. So this has after this 180 this tau time period of 2 by 4j, it will basically become it will have an angle between these two nuclei will be pi. So and also the populations are inverted as in SPI, and also we can see that there is an enhancement. Okay. So that is why here also, here what we can see that same thing has happened, 2 delta minus 2 delta, and the other one has become 2 delta plus 2 delta. But we are not the disadvantage that was there in SPI, that we have to selectively excite one of the nuclei or invert one of the signal of one of the nuclei, that is now removed, right? That is now removed. So because we are applying this 90-degree X pulse hard pulse, which will excite both the A and the X nuclei simultaneously. Okay. So if it is a case of a A2X system, then what will happen? Where this X nuclei will be first split into a doublet by this A nuclei, right? A nuclei. So first it will be a split. So the separation bit will be, what the difference will be, JAX, coupling constant JAX. Now again this another nuclei that is present, another A nuclei that is present, that will again split this one into two. Okay, so again this will be split. This one will again be split into two, into another W. You see the black signals. So now what is happening with this central line is getting cancelled. Because of this central line is getting cancelled, so this is a missing info. So this we are losing some information when it is a A2X system. For A3X, what will happen? The separation between this with a J3JAX, right? It will look like this. Okay. So INEPT, what is the advantage is that we can use non-selective pulses. We can there is gain with identical intensities for the two lines in the X doublet. Okay, and the disadvantages are that both the positive and negative signals are still present, and the missing lines in A2X system. These are the disadvantages, because we can see that the central line is getting cancelled. So this is missing line in A2X system. So answer this question in the INEPT experiment. In an AX system for the pulse sequence 90X A tau 180X, which is applied to both A and X nuclei, tau 90Y, the polarization transfer will occur from. This is a simple question. Even if you don't know, if you just know that polarization transfer of magnetization from a more sensitive nuclei to a less sensitive nuclei. So your proton is more sensitive nuclei. So basically, your transfer will take place from the proton to the carbon 13. Okay, this is more sensitive. This is less sensitive. So the transfer will take place from A to X. Okay, answer is this one, from A to X. Option D. Okay. Now for this, for overcoming those disadvantages, this refocused NEPT was developed. So this pulse sequence is, we are applying again another 180 tau 90 pulse. We are applying a second spin echo pulse. Okay, this one. So that the negative, now this anti-phase signals can come to in-phase signals. Okay, so the anti-phase will be converted to in-phase. This is the important point. So now everything you will get in the, you will be in phase, the positive signals only you will get. You will not have both positive and negative component. So refocused INEPT retains the original INEPT polarization. So everything is same, 90 tau, 180 tau, 90. on A, then X 180, tau 90. But it will add another spin echo refocusing block. This is the extra spin echo refocusing block, and this helps to refocus the positive negative components. So the last 90-degree pulse in the pulse sequence removes some artifacts and results in clean multiplets in the spectrum. So during the additional refocusing period, what will happen? The components will continue to evolve, and there the phase difference is removed. So the two components become aligned. Okay. So this is what was explained. So this after this anti-phase magnetization, after this 2 tau period, they will again refocus, and you will get in-phase magnetization. From anti-phase, you will get in-phase magnetization. So that was all for today. So in today's lecture, what did we cover? So today's lecture, we revised the concepts of solvent suppression, right? Solvent suppression. So there were three methods that we discussed in case of solvent suppression. One was pre-saturation that we revised. All these were covered in the lectures. Pre-saturation. Then we discussed about the jump return sequence, and we also discussed about the inverse recovery method. Okay. Again, we also learned Watergate in case of spin-echo. Then we also quickly discussed about the spin-echo concept and Spinico, what will happen? Chemical uh, shifts will get refocused, but if it is a coupled system, then chemical shifts will not be refocused. Okay. Then how we also learned about how we can determine the T2 values from Spinico experiments, because the relaxation will follow this e to the power minus 2t by 2 tau by T2. So we can actually determine the T2 relaxation time from Spinico experiments. And then we learned about the polarization transfer experiments. We also learnt about the exchange rates, how we can determine the exchange rates, and how is it related to the lifetime and the separation of the frequent chemical shifts of the proton in two different environments, of the nuclei in two different environments. So we discussed about NOE, and we also discussed about INEPT. Okay. So I hope we could quickly revise the concepts that were discussed in the lecture, and a few questions that were asked in your assignment. So that will help you. That will help you in revising the concepts. And if you have any doubts, you can go through the lecture once again. So if there are no further doubts, we can stop for today. Thank you so much.